Okay, so this is actually a flow phase diagram of a subject. Okay, on the previous slide, we're only talking about two phases, okay, liquid and the gas. Now we actually want to expand the idea into liquid, gas, and solid. We actually go through this. We plot out the P versus V as a function of temperature. So the things we went through is actually we went through this, pretty much just this. The one I just highlighted is actually the dashed regions we just go through. And then this line actually represents, okay, once it becomes liquid, then it's actually not so sensitive to the pressure, okay? So once you go to high pressures, the volume becomes actually pretty much just a constant. So the things we add more is actually right now we add in the solid phase here. So let's actually the PVT diagram, okay, we went through previously. So if you plot these things out in really 3D, okay, this is what it looks like. Okay, a little bit crazy, but you know, you want to learn how to read these figures. Okay, again, we just went through this, okay, in the previous slide. Right now we're in the solid components. One thing I want to mention here is that after we discuss so much things, we said assuming today you start from this point based on things you learned so far. What will be the phase of the points I just highlighted? Yes, it is liquid. What happens if I go from here to point X? See, it goes to a Tai-Yen area, right? So we know when you hit this curve, then I enter the two-phase coexist conditions. I cannot distinguish whether I have liquid or gas. And then if I keep going, change the volumes, then I know suddenly those things become gas. But what happens if you go from point 1, go to point 2, go to point 3, then go to point 4? When you go to point 2, what do you have? This point C is actually a critical point. Okay, if you go beyond the critical point, you enter the supercritical conditions where like you cannot distinguish what phases you actually have. It is a phase that no one actually know what we have over there. And then you keep going. What do you have here? Yes, you're going to have a gas. And then you keep going this, you go to lower pressures. Of course, this will be gas as well. What would you see in real time is actually, we know we start from point 1, which is actually totally liquid. You increase your pressures, you increase your temperatures. That's how you actually move from 1 to 2, right? And then you go beyond your critical points. Then what you're going to see is actually, okay, after liquid. Suddenly you become something that we cannot say what it is. Okay, we don't know the phase of that, but it just feel like a little homogeneous. And then you decrease the pressures, you lower down the temperature, and suddenly all the things become gas. If I draw like a few spots on this three-dimensional PVT curve, you want to know at what point, what the phase of that molecule is. Another thing what we are going to do is actually you want to look from this angle. We want to stack all these things together. What you're going to get is actually something like this. Let's go to the next page so you can have a better idea about what you're going to have. This is actually a typical phase diagram of a single component, okay? So all the things we talk about is single component. The axis is actually pressure and the temperature. And then you see all these lines, and then red lines. And those lines actually separate different phases. You should be able to identify that if you go to high temperature, most of the time you're going to have the gas phases. Vapor is actually very easy to understand because you go to really high temperature, most likely that region will belong to the gas phase. On the other hand, go to very low temperature, we know it's going to have the solid. So what are these lines? Those lines actually represent the Tai-Yen area, okay, which means it's going to have two phases coexist. So therefore you will know This line represents the solid liquid coexist highlight area. This line will be liquid gas highlight area. This one will be the solid gas highlight area. Once we know, okay, which region belongs to which phase, okay, the next thing is actually we can define some like simple terms. Assuming today you are actually at 1 bar or 1 ATM, you can draw a line across. Okay, so this is the liquid gas highlight area, right? So the corresponding temperature will be what? Normal boiling point. Very easy to understand. How about this? Solid to liquid. Freezing point or the melting point, right? Depending on how you define the directions. If it's like a solid to liquid, it's melting point. Liquid to solid will be a freezing point. One important feature is that for this solid liquid line, the slope is always positive, except water. Okay, water is actually the only materials that have this negative slope. Water is actually a very special element. With this knowledge, it actually already provide you many information. For example, okay, with this phase diagram, okay, let's think about some like daily life examples, okay. Assuming like you go to Rocky Mountains, go to a national park, we camp over there, okay, then we start to cook stuff. And then people always feel like it's more difficult to make the food fully cooked on the top of the mountain. Why is so? Okay, so if you know this phase diagram well enough, you can provide a very simple scenario. The way people judge whether I have a really hot water is whether the water is actually boiling or not, right? We also like to see all of bubbles coming out. So if you think, okay, I have a boiling water, okay, I dump things inside, and typically I just need to cook, like say 5 minutes, then it will be fully cooked. But if I do the same thing on the top of the mountain, it doesn't work. It's simply because if you go to higher mountains, your pressure is going to slightly decrease, right? Let's say you know the pressure is 0.9 atm. Then, if you draw a line here, you're going to see your boiling point is going to become lower, right? That means actually you only hit maybe to 95 degrees. You're going to start to see the bubble coming out. So even if you cook for 5 minutes, you're actually using 95 degrees to cook your food for 5 minutes. Okay, so therefore it doesn't work out. Your food is actually not fully cooked. With this very simple diagram, you can actually explain things that happen in your daily life. I want to use the very last few minutes to tell you, okay, what is the supercritical fluid and how it actually looks like. On this slide, okay, on the left is actually, okay, you can see actually a bunch of different molecules. And I list all these critical temperature, pressure, and volumes for you. Okay, you can see everybody is actually different. But how does it look like? So if you go from the subcritical regions all the way to the critical regions, on the leftmost panel, okay, you can see the differences, right? There are actually two phases actually here. Okay, I will call the bottom one as a liquid, top one is actually more like a gas. And if today you just crank up the pressure, crank up your temperatures, the difference between the two getting smaller and smaller. And after you go beyond the critical points, it becomes really homogeneous. People start to lose the judgment about, okay, what phase I actually have. That's what the supercritical fluid looks like. Okay, we actually don't know what the composition is. And the reason we cannot do that is because when people judge things exist in different phases, we actually use the refractive index. Okay, the reason you can see the differences is actually because the refractive index between two substances that are so different. When I say refractive index, what it really means is actually the density of the molecule, right? We all know the gas has the lowest density, liquid the second, solid the highest. So because the density change, we can see the phases, okay? But under such high pressure, high temperature, things just all mix together, okay? Even though they're actually very close to each other, because they are just so energetic that they won't actually form a just single phase. Okay, so it's very difficult for scientists to define what we really have after critical points. Okay, therefore we create a term called the supercritical to pretend that we actually know what's going on.